Welcome to Chapter 2, Building Science. If you really enjoy home construction, then you're really going to love the building science aspect. There's a lot of things that go into designing a home, making sure that it's energy efficient. I'm going to talk about all those different nuances that go into home construction to ensure that everything is super tight, energy efficient, the way everything should be. So first off, we have the building shell. And a building shell is just the outside exposed walls, roof, windows, doors, etc. So anything that really makes up the characteristic of the home. So if you look at the picture here, you'll see that there's nothing on the inside. It's just the framing. It's just the exoskeleton per se of the structure. That's what we consider to be the building shell. Moving on, we have the building envelope. The building envelope represents the parts of a structure that are in contact with both conditioned spaces. So if we look at the picture here, you'll notice that everything in green highlights the building envelope. So that is the interior structure, the places that are going to be comfortable, the conditioned space. Those are some of the words that we use to describe the building envelope itself. You'll notice that the attic is separated from that. The attic does get very hot. We're not going to condition that space. The heating and cooling system for the home is located up in the attic, right? So there's actually a system up there. That's one of the things that really makes this home unique and comfortable. Air takes the path least resistance. So if we were to have a centralized system in the basement like we do here, and that's trying to feed the second floor, I guarantee you that second floor is going to be uncomfortable. There's going to be hot spots. There's going to be cold spots. It's just really a poor design. So if you walk into a multi-story home and there's only one furnace and AC for the entire place, they're going to have problems. And unfortunately, there's not much that can be done. The only thing that I really can suggest is a mini split system to help condition that space. So we really have an energy efficient home here that we've incorporated. Building envelope, yet again, encompasses the green. There may be some times where the building envelope, you'll have a basement, and the basement just isn't part of that. There is no conditioned space. So you have to be careful when we start talking about conditioned or unconditioned spaces. Those are going to probably be the more terms that you're going to hear is conditioned versus unconditioned. So when we talk about it, the building envelope, we do have different parts that make up everything. That's the ceilings, the walls, the floors, the roofs, doors, and windows. All of that stuff encompasses the framework of the building envelope. Now, let's go ahead and dive into infiltration. Air leakage into the structure is called infiltration and is measured in air exchanges per hour, okay? So, or ACH. And so what we have here is we've got the air that's being sucked into our home, right? Air wants to go where it's warm, right? Heat is going to escape. And that's why we have these little arrows pointing of the cold trying to come into that nice warm. And it's really not the cold coming in, but more or less the heat escaping. But as the heat starts to escape up through the attic, right? Because of possibly poor insulation, well, we're replacing that heat with the cold being sucked into from the outside. And this does a really good job of explaining and showing the different paths where air escapes. We have outlet covers. Believe it or not, the wall cavity in between here have air that passes through there. And if these outlet covers aren't sealed, we're going to have issues with inside of our home. The chase here for our chimney, our exhaust piping for our furnace. Hey, we've got a lot of heat escaping up through here. You'll notice a lot of heat escaping up through the attic, going to the outside. We do want heat to escape during the summertime when we have lots of heat built up there from the home and the heat that is being blasted into the roof through summertime. And so we want vents up there to release this heat. However, we don't want that heat escaping during the wintertime. And so we'll talk about different things that we can do to help minimize the amount of heat loss that we have. So when we're talking about infiltration, there are technical terms that we like to describe structures. So then we have different definitions when it comes to our infiltration types. The first one is loose. So that means that we've got large holes in our structure. There's just large drafts. Maybe there's plastic on the windows, and that's really minimizing the draft. If we didn't have the plastic on there, it would feel very cold, or, just the heat escaping very easily. So that would be what we designate as loose. Semi-loose, we have a little bit less of infiltration, but we still have enough. We don't have the large holes that we can potentially see, but it's still somewhat drafty, not as good as it could be. Maybe we don't have enough insulation. Average is going to be our homes that are built anywhere from 1980s and on. Some of the building structures, the codes changed, and we're going to start to see, more energy efficient homes, and average is really the designation most of these homes do fit into. Loose, any homes that were built in the 50s, 60s, and before that, those tend to have not as great building construction. And so then we move on to semi-tight. Semi-tight is going to be anything that's like 2000 and greater. These homes have a little bit of building design to them to help ensure that we are minimizing the amount of heat loss or heat gain in our home. And then we do have tight. Tight is the strictest standards that our homes have, and those homes have almost no energy loss whatsoever. You'd be amazed at how well these homes perform. And so these key terms are important to know when we're doing our load calculations. And we're going to talk about what load calc is and why it's important. So then we also have the air barrier. An air barrier prevents or controls the flow of air between conditioned and unconditioned spaces. So we have air barriers. Sometimes they're called moisture barriers, and it's sometimes just a piece of plastic that's in the wall. Maybe when we're putting insulation down, there's that almost look like cardboard paper that's attached to the insulation. And those are all different types of vapor barriers or air barriers that help minimize that heat escaping, right? The less chances we have, or the smaller the gaps that we have, the less energy loss we're going to have, and we're going to have a more energy efficient home. Some things also, in addition to this, that are incorporated or considered an air barrier are drywall, right? If we just had stud spaces, then air can escape, move throughout the spaces without limit. So we put drywall in, that's going to really help mitigate the airflow from room to room. Rigid materials, so if we're putting any type of heavy duty boards or on the exterior, that's going to definitely help. So plywood sheathing, and then spray foam. Spray foam is something that's come about within the last 10, 15 years or so. A lot of homes are turning to spray foam, and what that is, it's just a foam that comes out as a liquid. Once it hits a structure, it does expand, and once it starts to expand, it generates or creates a insulation or a barrier from that structure and the elements. Spray foam, really good, fantastic product. However, you just have to be careful with it. If it's overdone, it could cause some major issues. Some people are trying to create conditioned spaces up in their attics. They just figure, hey, it's another space, and so they're going to spray foam the ceilings and so forth, and now all of a sudden it becomes part of the square footage of that home. So one of those things that we have to understand and know when it comes to especially building design, load calculations. Spray foam will have a big impact on how things work. So we do have a couple of pictures here, all right, of air sealing. Air sealing is a process of sealing the structure to reduce or possibly eliminate unintentional air infiltration into a structure. So we were talking about vapor barriers. Vapor barriers are great. However, you'll notice that when we put up the drywall or any type of paneling, there's still some gaps up there, and we want to make sure that nothing really comes through. So when I was talking about this spray foam, well, this orange stuff up here, that is all spray foam. All right, it comes out as a liquid, it dries, it expands, and creates a barrier from moisture, air getting through. I wouldn't say, hey, we need to spray foam our entire house. It's going to be leak proof and all that. No, that's not what it's intended, but it's more or less intended for ensuring that heat doesn't escape. Sometimes you may see it around windows, doors, that sort of thing. Another thing that we can use is house wrap. House wrap is just basically a piece of paper that they install on the exterior of your home prior to putting of siding or exterior cover on your home. That's going to help keep the air from coming through. Spray foam, we've talked about that. Weather stripping, that's just some foam that they can put in different places, yet again, to mitigate the amount of energy loss. We have mastic polyurethane. That's just a flexible type of paint goop that you can put onto things to ensure that things don't come through. Joint compound is what we use to seal the drywall up together, just to make sure that those cracks are uniform. And then once you paint the joint compound, it looks like a one piece, right? A caulking, right? We use caulking to ensure that those gaps that are we can't spray foam or we don't have access to anything like that. Caulking does a really good job of filling things in. The other bottom picture that we have here, this is all spray foam insulation. So that was done to the underside of an attic, and now that space can become a conditioned space. So they can potentially put drywall up there, do whatever they want. It looks like they're on the process of doing something. They have a little light fixture right here ready to go. So this space will be considered a conditioned space, which does add value to your home. However much square footage this space is now will be considered, because it is going to have heating and air up there. So one of the downsides of making a very energy efficient home with spray foam and so forth is that we don't have air coming and going out of our home. So the previous slides showed that air was infiltrating. Yes, we're losing heat because our heat is escaping. However, we're bringing in fresh air into the home. And that's important because, hey, we all get sick. We all need certain amounts of fresh air into the space. And that just happens naturally in some of these loose, semi-loose homes. We don't have to open up windows. So once we start getting into these new tight homes, we have less air exchanges per hour. And so now all of a sudden we have to bring in outside air, which is supposed to be cleaner and healthier. And we do that via an ERV. I know we talked about an ERV last time, but this is how it actually works, right? So we bring in fresh air from the outside. It goes through this filter, this heat exchanger, and then we're able to deliver fresh air to the inside. We take stale air from the inside, we bring it back through the filter and the heat exchanger, and we dump it to the outside. Well, the reason for this little heat exchanger is we're conditioning the air. Think about a day in Chicago and it's negative 10 degrees. I don't think we want to bring in that really cold air from the outside in. Or if it's a rainy day, we got a very humid day, we don't want to bring that moisture in. So the heat exchanger, it's going to remove the humidity, adjust it to the appropriate levels. It's going to make the air also closer to the design temp of what we have going on inside of our home. So now all of a sudden we're not getting blasted with really hot or really cold air. And so we see that heat transfer taking place over here. We're removing the moisture, we're moving the heat to the place where it belongs, depending on whether it's going in or out. And now all of a sudden we have just a more comfortable environment, and we're bringing in nice, clean, fresh air. One of the other things that we need to consider is mechanical ventilation. So when we have mechanical ventilation, we have these big old range hoods that look fancy. However, if they're moving, let's just say 1,000 CFM, guess what? We need to replace that. And so when this fan starts running and we don't have air coming in, whether it's an ERV or anything like that, all of our indoor air is just getting sucked out. We're creating a negative pressure in our space. And when we have this negative pressure, guess what? All this air starts to seep in from the outside, finding whatever little way it has into our home. And so now we're losing that conditioned environment. And now all of a sudden we're going to have a cold area because we wanted to run this big range hood. So just because this range hood looks cool in your kitchen, make sure there's a way to bring in the equivalent air that you're going to be sucking out. Otherwise, we're going to find air coming in from places that we really don't want it to come in from. So we have different construction techniques when our homes are being built. Granted, this doesn't necessarily apply so much to HVAC, but it's good information to know because it does have a factor in it. It does affect how we go about designing and building our systems. We need to understand these different premises to size equipment appropriately. So every part of the home has an effect on building performance, whether we realize it or not. And it's all about the construction of the home, right? So looking at flooring, whether it's wood flooring, tile flooring, carpeted flooring, that all plays a factor and a role in how that affects performance. We also have walls and insulation. Walls, how thick the walls are, how much insulation's in the walls, the type of insulation, all that factors into, yet again, how much heat we're gaining or losing. Windows and doors. Sure, a cheap window may be an alternative to, an expensive one. However, that cheap window, maybe it's not going to produce as much, or it's not going to help mitigate the amount of heat loss or gain that we're getting, that we receive. And so there's going to be energy loss there. So what you think you're saving initially may bite you in the booty in the long term. Attics. Attics are huge, right? There's so much heat that's being absorbed by the attic in the summertime. And even in the wintertime, you'd be amazed that it may be 10, 20 degrees outside. You go up in the attic and you may be relatively comfortable. And that's just how much heat is being generated from the sun, and it's just getting trapped up in there. Or it's even heat being, escaping from inside of our home going up into the attic. So having good insulation up there is key. Appliances, right? We have a bunch of appliances. You've got your freezer next to your fridge, next to your beverage cooler. That's a lot of heat that's, being moved around with those appliances. Big old electronics, TVs, things like that. That all plays a role in how much energy we need, how much heat is being generated, right? Lighting, having lots of lighting, Sure, we have LED bulbs and so forth nowadays, but guess what? The more lighting that you have, the more heat you're, introducing into that space, and we need to think about all that. So that brings me to heat load calculations. Heat load calculation determines the heat gain and heat loss of a structure. So we have our sun. Our sun is beating down on our homes, and that heat wants to come in. We are doing our due diligence by conditioning that space. Heat and cold, they keep playing with each other. The heat wants to go where it's cold. And so now all of that heat wants to come in during the summertime. And it comes in through floors, walls, ceilings, window, doors, ducts, anything you can think of, that heat is trying to come in. And we're trying to do our best to ensure that it stays out. And heat loads are important because we need to understand what information is out there to size equipment properly. All right. Think of it this way. So if you were to go online and quickly find a heat load chart or calculator or anything like that, what you're going to find is something like this. Real simple. If you don't know, in Chicago, we're located right over here in this area over by Lake Michigan. That puts us into zone 4, which says that for every square foot of our home, we need 45 to 50 BTUs to make sure that we heat and cool that space. That may be the case in some places, but not in all. And the reason I say that is, think of two structures. We have a greenhouse that's all glass windows, and it's 1,000 square feet. And then we have a home that's 1,000 square feet, and it's completely underground. Both in the same zones. Doesn't factor in windows, anything like that. Who's going to require more heating? Who's going to require more cooling? These two different structures require different amounts of energy to make sure that we maintain different values. And so in order to figure out exactly what we need, and so now we actually have what's called a heat calculation. This takes into account everything that's part of the home and determines exactly what size heating and cooling system we need for that space. Being completely oversized, I think you guys understand what ends up happening. We're going to have a really high delta T. The temperature coming out of the furnace is going to be too high. That furnace is going to start to starve for air. We're going to crack the heat exchanger eventually. So there's lots of issues, and so we want to make sure that we're putting in not only the right piece of equipment to maintain comfort, but we're looking at energy efficiency. We're ensuring that that equipment is able to maintain a certain temperature and level inside the home without wasting energy, right? customers are going to be more comfortable. They're going to be happy with the equipment choice. So the load calculation over here goes into the different details, takes into account heating, cooling numbers. We're going to talk about that next lesson, how to properly do a load calculation. But you can see that, hey, our walls, our doors, our ceilings, floors, all this is taken into account. Believe it or not, even the direction the home faces, how much sun gain is, we're achieving. All this goes into an account to determine exactly what size equipment. To be honest, this should be done on every single equipment replacement or installation. Just because there's a piece of equipment that was already put in there by the previous contractor does not mean it's sized properly. In my experience, it's probably been about anywhere from 85 to 90% of the equipment that's been installed has been oversized. And it's because contractors are scared that the equipment is going to underperform, or they just use a rule of thumb to size equipment and it's flawed. So we'll definitely go over some different values, like I said, in the next lesson to let you know what should be done. How do we do a load calculation? This is an example of a load calculation. Over here, we have a customer, and this is something that I wound up doing. I designed the home. Over here, you can see you've got room 32, 26, all that equates to a different zone. The different zones tell you how much heating and cooling you need for those different spaces. And now all of a sudden we can size the equipment properly. It's vital to ensure that things are put in. Yet again, I can't emphasize enough ensuring that the right size equipment is put in to begin with. Otherwise, we're going to run into major issues later on down the line. So let me go back here. This previous software, you have to literally build each room by room, draw everything out. It does take time. We have to know all of the structures, how it's all what makes up the structure, whether the walls are brick, they're stucco, do they have drywall, do they have siding on the exterior, what are the window types, how high are the ceilings. All these different values have an effect on the performance of the system. And utilizing this software here by Wrightsoft is fantastic. It's great. It's been around for a long time. It's a little bit archaic in the way it works, but it's pretty reliable. However, it's time consuming. Now, there's software out there. You can literally 3D scan the space, and within minutes, you're completely done. You go over to the sides, you check your different categories here, you put in different parameters, and then all of a sudden, it's going to spit out your value and let you know what size units we need. Really great for doing mini split systems, because mini splits, they're going to condition spaces, not necessarily entire homes all at once. So if I can get the values for each single room, it's perfect. Now I can determine what size unit we're going to squeeze in here to help make that room really comfortable. Energy audits. An energy audit is a collective inspection, survey, and analysis of a particular structure. So the energy audit is going to look at the structure, determine what the deficiencies are, and it's going to give you a list of recommendations to help make sure that you're not wasting energy. It could be all kinds of different things. We're going to look at the insulation values. Maybe we could put some more insulation up in the attic. Maybe we can seal things off. We're going to look at our mechanical system. Hey, how's our mechanical system running? Is it operating like it's supposed to? We're going to get our base loads. We're going to see how this equipment operates and have that data. And then we also look at health and safety. Maybe we're not bringing in all the fresh air that we need to. Maybe our home is really tight, and we're going to look at ways of making sure that we're bringing in that clean outside air that really is required. And then we have the first tool that is used in an energy audit, and that is the blower door. The blower door is a diagnostic tool used to measure a building's air tightness, help locate air leaks, and aid in the observation of air leakage characteristics. There's a big fan that literally attaches to your front door. A bunch of different sensors are located throughout it, and it's going to basically suck air out inside of your home and determine how much that pressure level drops. It's a very simple test to determine how tight our home is. Remember those 5 characteristics that we talked about, the loose, semi-loose, average? That's how you determine how tight a home really is. We have to do a blower door test. Sometimes we can do our due diligence. We just know the codes and what a semi-loose home looks like or a tight home looks like. But to really know for sure, we're going to do a blower door test. The next test that may be done is a duct leakage test. The duct leakage tester is a small version of a blower door used for testing duct system tightness. Similar principle, we're going to pressurize the system. We're going to look and see how much leakage is developed or how much leakage we see per se in the ductwork, and then we can go ahead and make recommendations on fixing that leakage. Remember, if we have a leaky air duct, that heating or that cooling that we're generating from the system, guess what? It's escaping into our home. Maybe it's escaping in the attic. Maybe it's escaping into our ceiling cavities. We just don't know. And that's just wasted energy. So by sealing up some of the ductwork, that's going to really help maintain overall energy efficiency. Another thing that we can do is add insulation. Insulation is fantastic stuff. Make sure you wear the right PPE when you're handling it. It's not good to breathe in. The purpose of insulation is to slow the heat transfer process between the occupied areas of a structure and either the outside of a structure or unconditioned space. It's not there to stop the heat loss. We can't do that. But what we can do is minimize it. We want to ensure that that heat that we're creating is staying inside of our space as long as possible, or we're keeping that heat from coming in. That's insulation. The more insulation you have, the better off you may be. And I say maybe because there is a point of diminishing return. If you have no insulation in your attic and you put insulation up there, you're going to have more energy savings. But if you have an R60 level, and we're going to talk about R value, you add more insulation to that, it's not going to really do much for you. You already have a bunch of insulation. You're adding more on top of it. All you're doing is really spending more money than you're going to gain back. So what is R value? R value is the thermal resistance of a substance. Varies with thickness and density. So depending on the type of material, what we have, it's going to affect the R value. So if you look at our zone for insulation, we are in a zone 5. That brings us to a R38 to R60 value in our attic. So that means that we need to make sure that we put enough of that pink insulation up there. We have enough of the blow-in insulation, or we have spray foam insulation up in that space to maintain these different values. If we're looking at 2x4 walls, we want an R13, R15 value, 2x6 walls, 19 to 21, and then going over to floors and crawl spaces, we have R25 to R30. So if you ever purchase any of the insulation from the big box stores, you ever look at it, you'll see that there is a R value on the side of it telling you, hey, this is how much heat loss that you're going to achieve with the different R values. One of the things that's out there that the book doesn't mention is it's called AeroSeal. AeroSeal will seal up the ductwork. Traditionally, sealing up your ductwork, you would have to take some mastic, which is basically that flexible type of paint. It solidifies, it hardens over time after it dries out, and then you have a seal. You can use tape, you can use mastic tape, so forth. Unfortunately, with a lot of home construction, that ductwork's already in the walls, in the ceilings, hard to get to. So how do you seal up these leaky systems? Well, you use AeroSeal. AeroSeal is a patented technology that seals leaky air ducts from the inside using a non-toxic aerosolized polymer mist, eliminating the need for invasive repairs and significantly improving HVAC efficiency, indoor air quality, and energy savings by sealing holes and cracks in hard-to-reach areas. So basically what we end up doing here is there's a machine. It's got their product or their polymer mist inside there, and it literally gets blown in throughout the ducts. They seal all the ductwork off where they can, where the registers are, and now you have this encapsulated system, and they just pressurize this stuff in there, and the air is going to start to leak out. And where it starts to leak out, that's where this polymer mist is going to go, and it's going to start to build up and start to seal up some holes. And you'd be amazed at how big of these holes that the system can really start to seal up. However, one of the issues that I've encountered is because ductwork is so poorly designed in our area, if you start sealing things up, what's going to happen is your static pressure is going to start to increase. Our system had these leaky holes, and we set up our entire system based on these on this criteria. And so now by sealing everything up, what ends up happening is now all of a sudden that air stays in, our pressure level starts to increase, and that may be too much for the system. So doing AeroSeal, you have to be very careful on the type of system that you have before you start doing it, because it actually could cause some major concerns. Having too high of a static on an ECM motor is going to cause that motor to burn out prematurely. I think AeroSeal, I haven't personally dealt with it. They're probably going to check the different values here to make sure that the system can handle the AeroSeal aspect, but you just want to make sure. Don't start sealing things off thinking you're doing something good when you're actually making the system worse. New construction, it is code. All ductwork has to be sealed, so you may not necessarily have to do AeroSeal on the new stuff, but the old stuff, it's a possibility. Windows come in a variety of shapes, types, and styles. Some even come with a gas in between glass panes to help with the R value. So you may have a inert gas like argon. That really helps with the R value of windows. Windows are inherently heat transfer monsters. They don't have a lot of R value in them because, hey, it's just a piece of glass, right? And so heat is going to go through these relatively easy. You may have seen it before. By building or changing the construction type of the windows, it does have an effect on performance. So originally we had single pane windows, single pane. There's not much to it. That heat just came, blazing in. Then they created the double pane. Now all of a sudden you have this little bit of an air gap between them. That really has helped stop that heat from coming into the space. You may fill up that little space with argon, and that really helps increase the R value. And then if you're really nutso, you can put in triple pane glass. That's really reserved for really high-end situations where there's a lot of heat loss, heat gain, or people that just want to spend high-end money on their windows. Going back to how the windows are categorized, we have either fixed windows, which basically means the window does not move, and then we do have operable windows. So operable windows do open and close. There's weather seals in there. Things can potentially leak in much easier, and so there are different values when it comes to heat load calculations between operable and fixed windows. And then we have Energy Star. Energy Star identifies products, homes, and buildings meeting strict energy efficiency criteria, helping consumers and businesses save money and protect the environment by reducing energy use and emissions without sacrificing performance. So going back yet again to our house, if our envelope is very tightly sealed, where we have very minimal loss, well, guess what? We can potentially get this Energy Star certification. It's very difficult to achieve. There's lots of different things that need to be done when we're building, constructing homes. However, the Energy Star does give it a certain level, which basically means that, hey, we're going to have a lot less energy required to condition that space. And you'd be surprised at how much smaller the equipment can be for an Energy Star rated home. Traditionally in our area, you're going to find a 3-ton air conditioner and about an 80,000 to 100,000 BTU furnace. Same area, same house, Energy Star rated, you may be in the 40 to 60,000 BTU range for a furnace, to 24,000 BTUs for an AC for an entire same size house. It's crazy at how much sealing, closing things off really does to help the efficiency of a home. And then there is the Building Performance Institute, the BPI. BPI certified contractors analyze the entire home to ensure HVAC systems work efficiently in conjunction with the building's envelope. So they're looking at the whole project. They're looking at the entire home, looking at different areas that could benefit from making sure that we are not wasting energy where it could be potentially saved. So they'll look at your attics, your mechanicals, they'll look at all kinds of different things to ensure that we're doing the best that we can. BPI does offer classes. They have different types of certifications out there. This really gets into that super nerd area of home construction, and it's important to know this stuff. And you don't even have to get to that really super nerdy level. You can learn just the different basics about building science to make sure that we're doing things as best we can so the customer enjoys their home as much as possible. A lot of the stuff that we really talked about here is a little bit outside of that whole HVAC world. It's important to know because it's going to have impact on our system design. Doing those load calculations, we need to understand the different materials and how they're put in and so forth. And we may not even have control over that. That may be done by the contractor, and all we're coming in to do is install the mechanicals, maybe the ductwork. We still need to size that equipment based on all these different parameters. So understanding all that is going to help us in the long term, because then we're not putting in the incorrect sized equipment, because then it falls on us as the HVAC contractor. So knowing a little bit about everything here does go a long way. And that is the end of this chapter. So hopefully you learned a lot regarding building science.